Hello, this is part 3 of chapter 3. We're going to start here with section 3.7, limiting reactants. Limiting reactant, just like in a chemical reaction, is the substance that is used up first. So whenever you have two or more things coming together in terms of reactants, one of them will run out first. We call it the limiting reactant. And the other reactant that is not the limiting reactant would be called the excess reactant, or you can say reagent. Before delving into chemistry, an example here would be with a bicycle. Here we have let's see, we have 4 frames. We have 3 pedals. 1, 2, 3, 4, 5, 6, 7, 8 wheels. So the formula to make a bicycle is 1 frame, 1 pedal, and 2 wheels. So if we were to put all these together, the maximum amount of bicycles we could make is 3 bicycles. The excess reactant, the ones that's left over, would be the frame and the wheels. And the limiting reactant would be the pedals. So again, limiting reactant is the one that will run out first. In this case, if another example with hamburgers, if we had 1 meat plus 2 buns plus 1 cheese plus 2 tomatoes as our formula to make a hamburger, we could visually see and say that a maximum that we can make is 3 hamburgers. Our limiting reagent would be the meat, because the meat would run out first. We can't make any more than 3 hamburgers because we would run out of meat. And the excess reactants would be the buns, 2 buns, 1 tomato, and 3 pieces of cheese based on what we were given at the beginning. Now visually this might seem easy. You can see what runs out first. But when you do chemistry in terms of the limiting reactant, and in this case you can even look at whether it's bicycles or hamburgers, you have to look at each case separately, meaning that the 3 buns here on our left, the maximum amount of hamburgers we can make is 3. The buns here, we have 1, 2, 3, 4, 5, 6, 7, 8 pieces of bun. The maximum amount of hamburgers we can make is 4. Cheese, 1, 2, 3, 4, 5, 6. So the maximum amount of hamburgers we can make is 6 hamburgers. And tomatoes, 1, 2, 3, 4, 5, 6, 7. We can make 3 hamburgers based on our formula here, because we said in our formula it takes 2 tomatoes to make our hamburger. So we'd have to compare each one, or we can say 3.5, I'm sorry, because we have 3.5 hamburgers because we have 1 left, 1 tomato left. So in this case, we compare with all our values. We would compare 3, 4, 6, and 3.5. And we would say the maximum amount of hamburgers we can make is 3. So that's very important when we are doing limiting reactions. We have to consider each case separately in terms of the reactants. Again, limiting reactant is the one that's used up first. The excess is the ones that's left over after all the reaction is complete. As I just mentioned, you need to calculate the amount of product formed from each reactant present. The limiting reactant that gives the least amount of product is the limiting reactant. And the amount of product is determined by the calculation from step 1 with the limiting reactant. So the limiting reactant will tell us the maximum amount of product that we can make. So in this case, as I just showed you earlier, 3 pieces of meat gives us 3 hamburgers, 8 buns gives us 4 hamburgers, 6 pieces of cheese can give us 6 hamburgers, 8 pieces of tomato can give us 4 hamburgers based on our formula that you need 2 tomatoes to make a hamburger. The limiting reaction is the meat, because we can only make 3 hamburgers. The maximum amount of hamburgers we can make is 3. Therefore, the meat is what governs how much hamburgers we can make. 3, the meat is the limiting reactant. Let's take this idea to chemistry, where we have here magnesium solid plus chlorine gas gives us magnesium chloride. How many moles, how many moles of MgCl are produced when 1 mole of Mg reacts with 1 mole of Cl2? We would take things step by step. If we look at this, if we had 1 mole of 1 mole of magnesium, we'd figure out how many moles of MgCl can be produced. So the top would be, if we looked at our balanced chemical equation, again, you have to figure out if the equation is balanced, and we say yes, it is balanced. 1 mole of magnesium and 1 mole of MgCl2. MgCl2 for every 1 mole of Mg. Okay, so this gives us, again, they cancel, the Mg's cancel, and we're left with 1 mole of MgCl2. Okay, so how many moles of magnesium chloride can be produced when 1 mole of Mg reacts with 1 mole of Cl2? The answer is 1 mole of MgCl2. Both reactants will give us a maximum of 1 mole of MgCl2. Just erase. Again, these are found on the Common Blackboard assignment, Blackboard Common website, link or account under my organizations. So the next one, part B, how many moles of MgCl2 are produced when 1 mole of Mg are mixed with 1.5 moles of Cl2, the limiting reactant, and which one, how much excess is left over. So if we look at our equation, 1 mole of Mg, again, we looked at our equation here, for every 1 MgCl2 for every 1 mole of Mg. This gives us 1 mole of MgCl2. Conversely, if we look at the yellow one, the 1.5 moles of Cl2, 1.5 moles of Cl2. If we look at the ratios, again, it's a 1-to-1. So 1 mole of Cl2 will give us 1.5 moles of MgCl2. So again, we have to calculate both reactants. And once we come up with the answer for both cases, we compare the MgCl2, 1 mole of MgCl2 versus 1.5 moles of MgCl2. The maximum amount of MgCl2 that we can make is 1. So I'll repeat what I just said. The maximum amount of moles of MgCl2 we can make is 1, and therefore the limiting reagent is the magnesium. We can't make any more than 1 mole of MgCl2 because we would run out of magnesium. How much excess reagent is left? Well, if you make 1 mole of MgCl2, that will take up 1 mole of Cl2. And if it takes up 1 mole of Cl2, how much do you have left over? You start with 1.5 minus 1 that you used up equals to 0.5. Will be left over, excess reagent, Cl2. The third question, how many moles of MgCl2 are produced when 1 mole of Mg reacts with 5 billion zillion moles of Cl2? Well, you can only make 1 mole of MgCl2. The limiting reagent would be magnesium. Another example with moles. How many moles of HCl, hydrochloric acid, can be produced from 4 moles of H2 reacting with 3.5 moles of Cl2? What is the limiting reagent? So again, the balanced equation here, H2 plus Cl2 gives us 2HCl. We have to look at each reactant. So here we have 4 moles of H2. We want to figure out how much HCl we can make. So 4 times 2 divided by 1. Where did I get this 2 and 1 from? That's from our balanced chemical reaction. 2 here for every 1. So when I multiply out 4 times 2 divided by 1, it gives us 8 moles of HCl. I do the same thing with the Cl2. Again, we have to do both reactants. 3.5 moles of Cl2 multiplied by 2 divided by 1. Again, I got this from the balanced chemical equation, gives us 7.0 moles of HCl. So what is the maximum amount of HCl we can make? The answer is 7 moles of HCl. If we make any more, we would run out of the Cl2. So the limiting reagent is Cl2, and the maximum amount of product we can make is 7 moles of HCl. So I'll let you guys have a try here. The question is how many moles of Fe2O3 can we produce from 16.8 grams of iron and 10 grams of H2O. So I'd ask you to pause the video, give it a try, and we'll go through it in a second. So I'll just set it up for you. I won't do the math. You'd have 16, we have to do each reactant separately. So 16.8 grams of iron. The first thing we need to do is figure out how many moles of iron we have. So we would divide this by number by, I'll calculate for you, mole of Fe, the amount of iron, the molar mass, 55.8. Where did we get this number from? That's from the periodic table for iron. Once we have the moles of iron, we will multiply by the ratio between iron, and we're going to select here the Fe2O3. So what is the ratio? It's a 2-to-1 ratio. So the 1 goes on top of Fe2O3 in the numerator. In the denominator, 2 moles of iron, Fe. And this gives us a value of 0.15 moles of Fe2O3. We have to do the same calculation for water. So I'll verbally tell you it's 10 grams of water divided by 18 grams of water, which is the molar mass of water, divided by 18, multiplied by 1, divided by 3. And there we get a value of, when we do all that calculation, we get a value of 0.185 moles of iron oxide. Okay, so we have, this is for the second one, and for the calculation above, it's 0.15 moles. Again, this is on another file on our common SEC 201 Blackboard account. So what is the maximum amount of Fe2O3 iron 3 oxide we can make? It's 0.15. What is the limiting reactant? This number comes from iron. So iron is our limiting reactant. How much water is left? So if iron is the limiting reactant, water has to be the excess reactant. So we have, if we had 0.1, let me erase this. So if we have 0.15 from the previous question, 0.5 moles of Fe2O3, we need to figure out how much water is used up to make 0.15 moles of Fe2O3. So we do that, we work backwards. 3 moles of H2O for every 1 mole of Fe2O3. And then once we have the moles of H2O, we need to multiply by 18, which is the molar mass of water of H2O. Remember, molar mass for grams per mole. And this gives us a value of 8.1 grams of water. So this is how much water is used up to make 0.15 moles of Fe2O3. We want to figure out how much is left over. So when we do 10, which is how much we started with in the original question, minus 8.1, we get roughly 1.9 grams of water left over. So those are the instructions. Calculate the moles of Fe2O3 formed from each reactant. This is for part A. You have to compare the two values. And we found out that iron is the limiting reactant. Less Fe2O3 is formed with iron, so the limiting reactant is iron. I'll give you guys another try, so you can just pause. How many grams of, remember the name, barium sulfate, can be produced from 200 grams of barium nitrate and 100 grams of sodium sulfate? So again, we have to figure out each reactant separately. I'll let you guys give it a try. With the barium nitrate, if I have 200 grams of it, so I'll walk you through verbally. You have to first find out how many moles of barium nitrate. So 200 grams divided by 261.3 grams of barium nitrate. I got the 261.3 from the periodic table. And then you have to look at the ratio. It's a 1:1 ratio. So you multiply by 1, divided by 1, and you're left with 0.765 moles of BaSO4. But as I said at the beginning, you have to do the same thing with the sodium sulfate. So with the sodium sulfate, if I start out with 100 grams of sodium sulfate, I again find the molar mass from the periodic table, and I determine it to be 142 grams of sodium sulfate. I multiply by the mole ratio, so 1:1, and then I got a number of 0.7704 moles of BaSO4. So which one is the limiting reactant? It would be sodium sulfate, because this one gave me less product. The maximum amount of product we can make is 0.704 moles of BaSO4. The question is, how many grams can be made? So if I have moles, if we have our roadmap with you, we have moles in the middle, you want to get to the mass, you have to multiply by the molar mass, which is 233.3 grams of barium sulfate, and we get 164. Again, all of this is explained in detail on the file on our common account for SEC 201. So sodium sulfate is the limiting reactant. Part C, how many grams of excess reactant is left? So in this case, we have 0.704 moles of barium sulfate you first have to figure out how much barium nitrate is used up. So I will again use the ratio. It's a 1-to-1 ratio to get us the moles of barium nitrate. And once I have the moles, I multiply by 261.33 grams of barium nitrate, which is the molar mass from the periodic table, and I get 183.97 grams of barium nitrate. Once I have the grams of barium nitrate, that's how much is used up. We have to figure out how much is left over. So from the original question, we do 200. We start with 200 grams of barium nitrate, subtract 187, and we get our value of about 15.9. I think I got about 16 grams left over of barium nitrate. Another topic in limiting reactant section is something called the percent yield. So here we have a box of percent yield is actual divided by theoretical times 100%. Whenever you do a chemical reaction, you can sit down and calculate how much product you would make in theory. So you can go home and sit at your desk and calculate out if I started off with for instance, if I start off with 5 pieces of bread, 2 pieces of cheese, I would know how many sandwiches I can make in theory. But if you were to actually do the experiment, if you were to actually go make that sandwich, maybe you dropped the piece of bread on the floor, so you have to throw it away. Maybe the grilled cheese sandwich got burned. So the actual yield is always going to be less than the theoretical. I'll repeat. The actual will always be less than the theoretical yield. The actual, as the name suggests, is when you do the experiment. In chemistry, there could be some side reactions. You could, spill some of your reactions, so you will never get 100% yield in theory, or in actuality, I should say. So, like as I said, actual yields are often lower due to side reactions, loss of product, when you're trying to isolate or transfer the material. So if you ever do a calculation using percent yield and you get over 100%, you should be a billionaire if you ever came up with some ideas like this. Just kidding. So the question was calculate the percent yield. So the percent yield is given to us at the bottom here. Actual yield minus divided by theoretical yield times 100. They tell you in the question 125 grams of aluminum gives an actual yield of 100 grams. So that's half the problem. You're given 100 grams as our actual, and it's our goal to find the theoretical. So you're given 125 grams of aluminum. Remember, you have to check if the equation is balanced. Yes, it's balanced. So we have 125 grams of aluminum. The first thing is to convert to moles. So if you're given the mass, you want to find the moles, you have to divide by the molar mass of aluminum. So divide by 26.98. Where did I get that number from? I got that from the periodic table. Once I have the moles of aluminum, and you don't have to write it out in one straight line, you could do it step by step. Once you calculate the moles of aluminum, you can divide by 2, a ratio of 1 to 2, because for every 1 mole of aluminum oxide, there's 2 moles of aluminum. So you divide by 2, and then you have the moles of aluminum oxide. You multiply by the molar mass of aluminum oxide, which is 102, and hopefully we get here our value of 236.3 grams of aluminum oxide. When you plug that in as our theoretical value, This is a theory. If we were given 125 grams, how much in theory could we make? We can make 236.3 grams. When we actually did the experiment, we only made 100 grams. So when you do the calculation, the percent yield is 42.32%. I want you to give it a try again, so you can pause the video here. And here we ask to calculate the percent yield of silver bromide if 375 grams of the actual compound are prepared from 200 grams of magnesium bromide. So you pause right away. The actual here is, well, I'll let you figure that out in a second. Is 375 grams, yes, of silver bromide. So you need to figure out the theoretical. So again, I'll walk you through it. So you start with 200 grams of magnesium bromide. You have to determine the moles of magnesium bromide. So you divide by 184. Again, 184 is the molar mass of magnesium bromide. You have to look up the molar masses. Then you will multiply by the ratio of 2 to 1. And that will give you 2.17 moles of silver bromide. This is not the final answer because we want grams. So if you have the moles of silver bromide, how do you find grams? Yes, you multiply by the molar mass of silver bromide. You have to find that from the periodic table. The molar mass is 187.77 grams per mole. So you take the 2.17 multiplied by 187.77, and you get 408.02 grams of silver bromide. Again, we have our actual, which is 375. We have here our theoretical here, which is 408.02. You plug it into this equation and hopefully you get 91.91%. So I believe that ends chapter 3. And we'll move along to chapter 4 in a